Hi everyone! Welcome to Hands-on Data Analysis with Python. I am your fun tutorial guide, Sarah Guido. It is pronounced Guido, not Guido. So the materials for this tutorial are on my GitHub. I guess the URL is a little bit hard to see. If you go to my GitHub, just github.com/SarahGuido. It's going to be this one right here, hands-on analysis, Python. So let's just go there for a second. And you can clone this repo. I'll let everybody get there, and let me just introduce myself. So I'm a data scientist at Bitly, where I'm doing fun Bitly things. If you don't know who Bitly is, we do the link shortening and other fun things. I'm one of the organizers of the NYC Python meetup, as well as the PyGotham conference, which is a fun regional Python conference that happens in New York every year. So it's going to happen in August this year. So if you're interested in more Python conference fun, you should check that out. And you can find me on Twitter at Sarah_Guido. So I'm very active on Twitter. And I tweeted the materials to this, so. Let's talk about installation. So how many people in this room have used any of the tools we're going to cover today? Yes, a few people. Okay. This tutorial is going to cover like the basics of these different tools. So you might be a little bit bored if you've worked with pandas before. We're going to go over the basics because this is an intro tutorial. In terms of installation, the easiest way to install all of these materials that we're using is with Anaconda. So Anaconda is a scientific Python distribution. It comes with a lot of awesome tools. And it'll install the 3 tools and all of their dependencies. What are we doing? Pandas, scikit-learn, and matplotlib. So that's one option. Another option for installation is I have a requirements.txt in the repo, so you can just pip install that if you don't want to install Anaconda for any reason. So let's just take a few minutes and do that. Is there anybody who doesn't have these tools installed, first of all? A couple people. Okay, so awesome. Let's just take a few minutes and do that. So the way that I've structured this tutorial is we're going to sort of talk about it in the sense of a data analysis workflow. So we're going to start with Pandas, which is a really awesome data pre-processing and analysis tool. It has a couple of really awesome data structures that we're going to work with. We're going to spend quite a bit of time on that. Then after that, we're going to talk about scikit-learn, which we're going to use for some machine learning. So another bit of analysis. And then finally, we're going to conclude with matplotlib, which is a Python graphing tool. So we're going to make some plots. And we're going to learn all of these things, and then we're going to also use these tools on a census data set that is in the repo. So we're going to look at some fun stuff with that. Is anybody not or having problems with installation? Is anyone just totally I can't install these things at all? Okay, awesome. So I'm going to keep moving. If I'm going too fast for those of you that are still installing, let me know. So there are a few options for running the materials. Well, technically there are 2 options, which I'll explain in a moment. So option 1 is IPython Notebook. I will be using IPython notebooks throughout this tutorial. They look like this. Whoa, that's not good. Let's try that again. Oh yeah, I need to, yeah. So the way that you would start IPython Notebook, so once you're in the directory, you just type IPython Notebook, and it will launch. And then you can go into the Notebooks folder, and within the Notebooks folder are all the materials. So we have 4 different notebooks in there. The data analysis one is the one that we'll be using for the census data. The other 3 correspond to each of the different components, so pandas, scikit-learn, and matplotlib. Also, there's an answers directory which has the answers for all of the all of the stuff that's in the notebooks folder. Please don't look at the answers right now. Look at them later if you can't figure it out. Don't look at the answers first. And all of the data you need is in the data folder. So option 2, I gave this tutorial a while ago, and nobody chose option 2, so I didn't bother to really update it. It's basically just straight code files. It's really kind of cumbersome and inconvenient to run, so I don't recommend looking at that. Option 3, Wakari is a great platform for hosting IPython notebooks in the cloud. Unfortunately, I don't think that Wakari works with the latest update of IPython Notebook, which is now called Jupyter or Jupyter. So Wakari, the old version of this might be on Wakari, but the new version was not really working. It just kept failing, and I wasn't sure why. I'm not entirely sure the development status of Wakari is anyway. So the other option, if you've already gone to a tutorial today and you're kind of exhausted and you don't want to really interactively code because there's a lot of interactive stuff throughout this, option 4 is to just sort of follow along on the web. So I've put the 3 lesson notebooks on IPython Viewer, which is not interactive, but you can still read it, follow along, and see what's going on. Yes? What happens when you click? Okay. Also, it also depends on what version of IPython you're running. So if you're not running version 3, you might get some weird errors. So if we could all update IPython right now, I discovered this earlier that new versions of IPython don't work so well with prior to version 3. If you do have Anaconda, you can just type in conda update IPython, and I think that will solve all your problems. If not, I think it's pip install -u, or might be capital U for update, and then IPython. So let's see. Is anyone having trouble opening the notebooks or is confused about how to open the notebook? One person in the back. Can you raise your hand high, very high? I'm short. Oh, Dana, can you? Right there. Cool. Yeah. I have a wonderful TA today, Dana. Thank you so much, Dana. Okay. I also want to mention that within the README, there's a link to a document, and this is for questions. So the purpose of this is if you're not having like super like workflow delaying issues, maybe add your questions here, and then I can discuss them at the end, because chances are someone has the same question as you. We have a lot to cover, so this will kind of help mitigate the problem of falling behind, which we are just a little bit. Okay, so let's begin. If we all go into the notebooks directory, pandas. Load this up. Okay, so let's talk about the importance of data preprocessing. So data preprocessing, also referred to as data wrangling, data cleaning, data scrubbing, data manipulating, and so on, is probably the most important thing you're going to do with your data, because it sets the stage for everything else that you're going to do with your data. So the way that you process your data has a huge impact on all of the analysis that follows. So you have to really think about what your end goal is when you're preprocessing your data. And it's also a process for getting to know your data. You should be able to answer these questions about your data if you're going to do any sort of successful analysis on it. So what kind of data are you working with? Is it categorical? Is it continuous? Is it a mix? What's the distribution of features? Do you have missing data? Do you only need part of your data? Do you need more data? These are all questions that data preprocessing, the process of preprocessing your data, will help you understand. And once you know the answers to these questions, it'll be a lot easier for you to conduct analysis on it. So by far my favorite data preprocessing tool is pandas. Pandas is this wonderful data wrangling, modeling, analysis tool. It's really similar to R in Excel, if anyone's used R in here, or I'm sure a lot of you have used Excel. The data frame structure in Pandas is actually named after the data frame structure in R, if you've used with that. And Pandas data frames look sort of like SQL tables, which we'll see in a moment. We're going to discuss both the series and the data frame today. And I should say that the way that I've structured this is we'll work through a section covering a topic. So the first topic is going to be data structures. And then we'll do a little lesson. And then we'll work through another section. I think the next one is like file I/O and exploring the data. And then we'll do another like mini lesson and so on. So there's going to be a lot of like interactive sections. Okay. So why would you want to use Pandas as opposed to those other tools? So I do everything in Python. The company I work for, Bitly, is a Python company. My previous company was also a Python company. And for me, it's just easier, especially if I have to continuously clean or process data. If it's already in Python, I can just build it into my process. It already exists. I also just really like writing Python. That's why I'm one of the organizers for the meetup group and I come to these conferences. It's really great for pre-processing too. It has lots of different tools. It works really easily with a lot of other parts of the scientific Python stack. So we'll also see it works really well with both scikit-learn and matplotlib. All right, so let's talk about some of these data structures. The first one we're going to learn about is the series. So the series is a one-dimensional array. It can hold a variety of data types. It can hold a mix of these types. It can be all one data type. It's really pretty easy to create a series. So this is how you create a series. First, we're going to import pandas as PD. This is standard pandas importing convention. You'll see it used frequently in anybody's pandas code you ever see. So here we have a list. It's just a list of some numbers. I've called it some numbers. The way that we create a series, you do pd.series, and you pass in the list there as a parameter. If we run this, we get a series. Pretty simple. So here are the values from the series. Along the left side here, this is the index. You can change the index. So if you didn't want your index to be numbers, you could also do that. So if you're creating a series, here we go, pd.series, some numbers. Here we're going to pass in this list of letters that we created up here. Index equals IND. If you run that, now we have letters for our series index. If you wanted to know what your series was, you can do that using the index attribute. It's pretty easy. You can also do this with the values. So if you want to see what the values were, it's the values attribute, and it'll return that in an array. So you can create a series with the dictionary as well. Here we have a dictionary called more numbers. So you have your keys, 9, B, 8, and your values. So once again, we can pass in multiple data types to a series. So here we have integers, floats, and a string. And it's just the same thing again. You pass in that more numbers into the series object. So if we run that, now we have a series with different data types. Cool. So now let's talk about the data frame. Data frames are awesome. So the data frame is probably Pandas' most used data structure. So it's basically two or more series combined into one. It can hold a mixture of data types again. It looks very similar to a spreadsheet in Excel or a SQL table in that you can see column names along the top and it has an index along the left-hand side. So again, there are several methods of creating a data frame. So you can do it by combining series. So here we have combined series, pd.dataframe. This is the data frame object. And here we pass in a list of series. If we run this, now we have two series. You can see that our second series was not quite as long as our first series. So here we have not a number. So if you look in column B, we have both an integer and a string. So that's kind of interesting. If If you want to see what the different data types each column has, you can use the dtypes attribute. So if we run this, you can see column A is integers. Yes. Column B is an object. So whenever there are mixed data types, it returns the data type for the column as object. Here we have float, integers, and then float. Okay, so another way to create a data frame is with a dictionary of lists. Just like we created a series from a dictionary, you can create a data frame from a dictionary. So here's our dictionary. Our first column is going to say, I love pandas so much. Our second column is going to say, so will you, I promise. So we can take this whole dictionary and pass it into our data frame object. If we run this, there you go. So this is what a data frame looks like, right? It has column names along the top and our index along the left-hand side. Okay, is everybody good with that? Pretty simple stuff, not super complicated or anything. Okay, let's talk about file I/O. So this is one of Pandas' most awesome qualities. It's super easy to read data into Pandas from a CSV, from a text file, from anything basically. You don't have to iterate over the rows and store them somewhere. You can literally just pass the file into the read CSV function. So here we have a data set regarding characteristics of wine. So all we do to read that in is we do pd.readCSV, and this is the function that'll read it in, and then this head function here is just going to print out the first 5 lines. So we do this, super easy. No need to iterate over things or make CSV writers or anything like that. Okay, so reading in a tab delimited file is also pretty easy. You can specify the delimiter when you read in the file. So here we have a data set regarding miles per gallon of cars. So again, we use the read CSV function, pass in the file path, and then we set our delimiter to tab. We do this, cool. If we didn't pass in the delimiter, gross, not good. So need to pass in that delimiter. Okay, so now that we've read in our data frame, cool, let's learn some things about it. So you can easily see the number of rows and the number of columns a data frame has using the shape attribute. So if we run this, see our auto MPG data frame has 398 rows and 9 columns. If you want to see the last 5 lines, because we already used head to find the first 5 lines, now we can use tail to see the last 5 lines. If we run that, last 5 lines. It's also pretty easy to pull out the column names, just like in the series when we pulled out, well, no, not quite. It's really easy to get the column names, so that's just the columns attribute. If you run that, see a list of columns. You can also pull out the index using the index attribute. That's similar to what we did with the series, index attribute. So if you go back to columns, cool. So a really fun thing you can do is you can generate some summary statistics using the describe function. So this function calculates statistics like the mean, the standard deviation, and quartile values for any continuous and integer data in your data set. So it's not going to try and do this on your categorical data. It's only going to do it on the numerical data. So if we look at this, here you go. Super easy and a very nice way to easily generate some information about your data frame. So once again, along the top, we have the column names. Along the side, we have the count, how many rows we have essentially, the mean of each of those columns, standard deviation, and then the minimum value, maximum value, and then the quartile values in between. Okay. So another useful thing you can do is you can sort your data. So let's say you wanted to sort it by miles per gallon, and then you want to pull out the cars that have the highest mile per gallon. Sort automatically does it from lowest to highest. That's pretty easy. All you would do is you take your data frame, auto MPG, use the sort function. The column we're going to sort by is miles per gallon. You can sort by multiple columns if you want. And then we're going to grab the last 5 rows. So if we run this, or I'm sorry, yeah, highest miles per gallon. So right up to 46. It's pretty good. Okay, so now it's your turn. It's your turn to do some fun pandas on a certain data set. So there's a data set in the data folder about credit approval ratings. It's a little bit weird. It just has a bunch of letters and numbers because obviously this is very sensitive data. So I'm going to give you 5 minutes to work through this section. I encourage you to work with the people around you. We're all Pythonistas. We're all very friendly. So make some friends. And let me know if you have any questions. So we're going to take, 5 minutes. Okay, so let's go over this. I'm going to solicit answers from you guys. So, okay, how do you read in this file? Anybody? What? I heard it in the back. Yes. Okay, then how do I grab just the column names? Yes. Cool. Sorry? Yes. Oh, that means that the D type of our data frame is object, which means we have mixed data types. So we have some integers, we have some strings, we have some floats. Cool. Okay, so how do we find out how many rows and columns this has? Shape, yes. Cool. Oh, yes? That's interesting. Okay, let me come look at that in 1 second. Let me go through the rest of these first. Okay, so how do we look at the first 5 lines? Oh, you got it? Okay, cool. Head. Okay. Last 5 lines. Tail. Can you describe the data? Yes, you can. Cool. Notice how it only describes numerical data, so we're not trying to find the mean of column D, which is Y, U, Y, U, U. Describe which one? Oh, B. B is because later on in B we have a string character. Yeah. I should format that for next time. So that's why, because within B we have mixed data types. So it's not going to try and describe a column with mixed data types. Yes? I'm pretty sure that describe ignores missing data. There are ways to handle missing data as well that I don't think I have time to work into this, but yeah. So I'm pretty sure that it just is like, oh, it's not here, whatever. We're still going to figure it out. Okay, so let's sort on column H. df dot sort. Yep. So much fun. Cool. Column H, 0. And then we start getting higher. Okay. Cool. Now let's talk about working with data frames a little bit more. So Pandas has a ton of functionality for manipulating and wrangling and subsetting data frames. So we're going to look at a bunch of those ways. So there are multiple ways to select both rows and columns. You can access them by index, by slicing, by looking at the labels, to positions. It's so many different methods. So let's just look at selecting one column from a data frame. So let's take the miles per gallon column from the auto MPG data frame. So this works similar to how you would access values from a dictionary. So here we have auto MPG, square brackets, and then the column name inside. So if we run this, we get just the values as well as the index for the MPG column. You can also use the column name as an attribute. So you can do exactly that same thing with by typing auto mpg dot mpg. Okay, cool. To extract rows from a data frame, you can slice them similar to how you would slice a list in Python. So if we wanted to grab rows 7 through 13 from our wine data frame, here we would type the name of our data frame, wine, square brackets, and then our slice, 7 to 14. There we go. So Pandas has a couple of tools for more refined indexing. It has the loc indexer for label-based indexing. So the loc indexer takes input as, in square brackets, row and then column. So let's say we wanted to select the ABV value in the 8th instance in our wine data frame. So if we run this, we get 14.83. Here we have wine.loc, square brackets. We want the 8th row, and then ABV is the name of the column. If we look up here, we can see 8th row, ABV, 14.83. Cool, we have just done exactly what we thought we were going to do. You can also use loc to grab slices. It's important to note, though, loc interprets the index as a label. So that means that if your index is numbers, it says, oh, 0. The label for that row is 0. 1. The label for that row is 1. So this means that it's not the position. And this will be clarified in 1 second. So if we're going to grab rows 8 through 11, here we have .loc, square brackets, 8 to 11, like we normally would do a slice, and then the name of the column. When you run this, you see that we actually grab 11. This is because, again, we're looking at labels. So this would be the same thing as passing in, like, let's say this was A, B, C, D. Say A, it would look like this. You could pass in this. A, B, C, D, so on. That's how loc interprets these. Well, it looks like we're slicing. We're not actually slicing. We're accessing it by the name. So, as you might expect, we can also select multiple columns. Just pass in a list of column names into your loc. So we have our slice, or not our slice, our labels that we want, and then our columns. So here we have a very small subset. Okay. So if we want to grab, let's say, specific rows, but all of the columns, you would do this. So we have .loc, square brackets, we have rows 8 to 11, and then you would use just the colon to grab all of the rows. If we wanted to grab all of the rows but only specific columns, you could do it like this. It'd be the same thing. So you would pass in a colon for the rows, and then let's say ABV, hash. And we have all the rows and then just columns. So loc really provides a very refined method of targeting exactly the data that you want from your data frame. So another method that you can use to select data is with iloc, which is based on position. So iloc indexing works exactly like slicing a list works, meaning that if you pass in 8 through 11 in that rows position, you're only going to get rows 8 through 10 back because it's by position. So again, takes input as row and column, but it only takes integer input, so you can't pass in names because, again, position. So if we wanted to access the 60th row and the 6th column, which is our model value, it would look like this. We have auto mpg period iloc, and then the row, and then the column. If we wanted to grab rows 60 to 63, and then the last 3 columns, oops, this is going to grab not the last 3 columns. Yes, it is. Cool. Okay. We would pass in, once again, it's like slicing. So 60 to 64 to grab 60 to 63, and then 69 to grab these 3 right here. Okay, so let's grab all of the values in the last 3 columns again. Okay, once again, iloc, square brackets. We use the colon to grab all of the rows, and then a slice to grab the last 3 columns. Once again, if we wanted to grab all of the columns, you could do, let's say, that, and then this. And this would grab all of the columns but only 6 rows. Okay. So one of my favorite methods for selecting data is through Boolean indexing. So Boolean indexing is similar to where clause in SQL, if you've used SQL, in that it allows you to filter out data based on certain criteria. So let's say we wanted to select from the wine data frame where the wine type is type of 1. So the way to do this is you have your data frame, wine, square brackets, and then we want within the wine data frame where wine type is equal to 1. If we run this, scroll over, you can see now we have all of the wines, the wine type is 1. This syntax can be a little bit confusing, so let's look at a few more examples. This works with any comparison operator, like greater than, less than equal to, not equal to, and so on. So let's say we're going to select everything from the wine data frame where magnesium is less than 100. Once again, we have our data frame, square brackets. We want everything in the wine data frame where magnesium is less than 100. If we run this, here we have magnesium less than 100 right here. Okay. You can also say not equal to with the tilde. So let's say we want to select from the data frame, the wine data frame, where magnesium is not less than 100. So greater than. To do this, we have the data frame name again, wine, followed by square brackets. And we would have our tilde, and then in parentheses, the data frame wine where magnesium is less than 100, but not less than 100. Run this, magnesium is now greater than and equal to 100. Okay. So it's also possible to combine Boolean indexers, and you can come up with some pretty crazy subsetting doing this. So when you have multiple Boolean indexers within your index, make sure you enclose them in parentheses. This is the step that I usually forget, and then I'm like, why doesn't this work? Okay, so let's say we want to select from the wine data set where magnesium is less than 100 and the type of wine is 1. To do this, we have our data frame, square brackets for indexing, and our first condition, which is where magnesium is less than 100 in parentheses, and where wine type is equal to 1. So let's run this. So we have magnesium less than 100, wine type is 1. It's just like a where in SQL. So if you wanted to, you could, combine these together as many as you want. I'm not sure how many it will take before it's like, what are you doing? So here we're going to add on where ABV is greater than 14. So wine ABV is greater than 14. Run this again. Here we go. Now we have only 5 rows from our original data set. So we're getting more and more refined as we go. So another method of selecting data, and this is more to see if certain types or values exist in your data set, is the isIn function. If you pass in values to isIn, it will return a data frame of Booleans, either true or false. So true means that the value that you've passed in actually exists within that column. So let's look at the first 5 rows and check if some values exist in our AutoMPG data frame. So here we have just a list of values, 8, 150, 12.0, and then Ford Torino. So we're going to pass in, and here I've grabbed the first 5 rows from the AutoMPG data frame. So we're going to pass in that list of values to the isIn function for our AutoMPG5 data frame, and it returns something that looks like this. So it'll return true if within that cell, if that cell matches one of the values from your list. So here, these all have 8 cylinders. Here's true for acceleration, car name, Ford Torino right there. That's just sort of a way to see, okay, does this exist somewhere? All right, so let's try some of these ourselves. Oh, yes, question. Yes. Ooh, that's a good question. I'm gonna look for that while you do that, because that's actually a really good question. Um, okay, so for this lesson section, we're going to take approximately 5 minutes. Oh, wait, one more question. Ooh, that is another really good question that I'm also going to find out. Wow. Yes, one more question.
Also, can I get the result of the table where there are values? If I don't care which one of the columns fits the criteria.
Okay. Let me talk to you just a second. So, okay, for the lesson section, let's try some of these on that credit approval data frame that we were working with. So go ahead and work through these. I'm going to try and hunt down answers to these awesome questions, and we'll take about 5 to 7 minutes to do that. Okay. Okay, how are we doing? Do we need more time or are we good? Okay, cool. So I found something interesting. So back in our is in section, if you actually throw this part into an index for a data frame, it will return the values that return true that you passed into is in. So here we have cylinders are 8, acceleration 12, and then Ford Torino. Unfortunately, for everything else, it passes in not a number, which is a little bit annoying to look at, but it's kind of an interesting thing. Okay, so let's go through this. So how do we extract column C from our credit approval data frame? Like that. Data frame and then C. How do we slice rows 5 to 10 from the credit approval data frame? Yes. Cool. How would I look up the value for the 13th row in column C? By label. So, loc. Okay, I'm just going to do it. C. Here we go. Loc 13, comma, C. Okay, same thing by position. We would do df iloc 15 again. It's time 2, right? ABC 0, 1, 2. Yes. What if I wanted to select all data from our credit approval data frame based on column C being greater than 5? Okay, how would I do this? df, what goes in here? C. Greater than 5. Okay, cool. Greater than 5. Okay, I'm just going to copy and paste what I just wrote because we're about to add on to it. Okay, so column C being greater than 5 and column F being equal to W. And, yep, what am I missing? Yes. Woohoo. The most recent version of IPython Notebook, just like if you select and just type parentheses, it just parentheses them. Yeah, IPython Notebook is seriously cool. Okay. What if I wanted to look at a Boolean data frame where something is in something else? Let's just say value, no, vals. Have a list of values. Now we do is in vals. Cool. And if we wanted to return just the values, we can index it. Cool. Okay. Oh, sorry. Yeah. Yep. So just like we did, I'm going to scroll up for a second, up here where we have df and then square brackets and then inside what we're selecting. Down here I have df, square brackets, and then you can pass in the isIn function. Yes? Wait, sorry? Oh, well, yeah. I would say this is the 0th row, but that's just me. Maybe that's just me. Sorry if that was a little confusing. When I'm talking about zero index things, I say the 0th row. Am I the only one that does that? Yeah, okay. Maybe I'll change my yeah. Awesome. Good question, though. That could potentially be very confusing. Okay, we are running a little bit behind, so I'm I'm going to skip the group by section. I don't want to. We're going to skip the group by section. Yeah, very sad. That's okay, because now we're going to learn about merge and join, or how pandas can be like SQL, which is also quite fun. So in pandas, it's possible to combine data frames in series, much like you would in SQL. So for the examples in this section, we're going to work with smaller data frames that I've made up rather than our large data sets, because it's easier for me to provide proof of concept to you this way. So let's just start by appending a row to a data frame. So if you remember from above, we had a data frame that basically said, I love pandas so much, so will you, I promise. Let's add in, let's append a row. So we can do this by passing in a dictionary to the append function, and setting ignore index equal to true. So we've appended a row, dude. I love pandas so much, dude. So will you, I promise, dude. Cool. So that's pretty easy. That's another way to add to your data frame. Appending a column is also easy. All you have to do is you set your new column name equal to a list or a series. So here we have data. This is this data frame right here. We're going to say column 3 is equal to, how do you like, oh, OSCON. Oh, no. Yeah, sorry, I gave this at OSCON. I thought I changed everything. PyCon. Okay, there we go. How do you like PyCon? Great. It's the first day, so I hope you're having fun. So you can't add a new column to your data frame if it's a different length than the original data frame. So here we're trying to add column 4. I am too short. This is not going to work. We get an error. So you can't append rows like that. Oh, sorry, too fast? Oh no, where did the dudes go? You know what, I didn't to do this. Yep, you have to store that. Now this isn't going to work because, here we go, let's just, dude, great. Now we have a row of dudes. Just like in this room, we have rows of dudes. All right, anyway, again, this doesn't work. Sorry. Okay. Need some water. So you can merge in different ways, just like joining in SQL. So this can be a little bit confusing because there is also a join function in pandas, but join in pandas is different than join in SQL. Merge in pandas and join in SQL are essentially the same thing. So let's look at a taco data set that I made up. It's called tacos. I'm going to read it in. Great. This is basically the name of the person, their favorite restaurant, the number of tacos they can eat, and the rating that they've given those tacos. Okay, let's also look at an imaginary taco toppings data set. And then we're going to join these together. So here, once again, we have the person's name, we have their favorite topping, least favorite topping, and then corn or flour tortillas. Corn, obviously, but opinions are valid. Notice that we have a unique identifier in each of these data sets that's the same, the name column. So here we have name, here we have name again, and the same names are in both. So we can easily merge these together because we have this unique identifier. So you don't even need to pass the specific key to merge on. Merge will automatically infer which columns to use. So here we have pd.merge tacos and taco toppings. If you do this, great. Now we have name, restaurant, number of taco score, as well as favorite topping, least favorite topping, corn or flour. You can also do it like this, which is actually the syntax that I use everywhere else. Data frame, dot merge, and then the other data frame you want to merge with. So tacos, which is our first data frame, dot merge, and then our second data frame. Same thing, just a little bit easier to understand what's going on. So by default, merge performs an outer left join, left outer join, which means it takes the key from the left data frame, in this case, tacos, and matches the right to it, in this case, taco toppings. So generally speaking, full outer joins will join everything as a union, meaning that everything will be joined even if there are missing values. And inner joins will join everything as an intersection, meaning that if a value does not appear in a row, the row will be left out. So let's look at how this works. So let's append a row to our tacos data frame. And here I'm saving it to tacos, so it actually exists in tacos. Now we have Dan. If we did a full outer merge, I'm going to fix this. Apparently I did not fix this and commit it. Okay. First data frame, tacos.merge. Taco toppings. How we're merging, we're going to do an outer join. So if we do this, see down here, Dan exists in tacos. He doesn't exist in taco toppings. So even though he doesn't exist, he still gets merged into the whole data frame. If we do the same thing using a right outer join, which means we're only going to be merging based on who's in the taco toppings data frame, we're using only those keys, and Dan is going to be left out. So if we do this, no Dan, because once again, Dan exists in our tacos data frame, but not in the tacos toppings data frame. Okay. So join, different than SQL join, is a way for you to combine data frames without needing a key. So here we have taco extra, which contains data about chips and spiciness level. If we run this data frame has no names. So we can join this to our data frame, though, using the join function. So here we have tacos, first data frame, join, taco extra. Cool. And poor Dan, he doesn't have any chips or spiciness. Again, you can specify how to join. If we select inner, once again, we're only going to be joining based on, based on these 5 rows. Since Dan is in the 6th position, or the 5th position, however you want to refer to positions, no Dan in this data frame. Because once again, we're joining tacos to taco extra inner, which means we're only going to join on things that essentially exist within both data frames. In this context, it means the number of rows. So there are only 5 rows in taco extra, so we're only going to get the first 5 rows from tacos. It's possible to join more than 2 data frames at a time. So let's slice off the name column from taco toppings. So no more name. Here we have just favorite topping, least favorite topping, and then quarter flour. Awesome. So once again, we can join multiple data frames together. So it's still all an outer join. So even though there's no toppings or taco extra data for Dan, he's still going to be included. So we have our first data frame, tacos. We're going to join that to taco toppings no name, which is this no name taco toppings data frame we just created. And then we're going to join that to taco extra, which is the chips and spiciness tacos. So once again, here we have everything. Dan is included even though he has no toppings or no chips and spiciness level. Okay, so let's collectively merge some data frames. I've created another toy data set called pizza toppings, and pizza extra. So very similar to what we just did. So let's take, let me see, 5 minutes to work through this. Okay. Are we good to come back? Cool. So let's merge some data frames. Can you merge the following data frames together? Yes. Yes, we can. Oops. Whoa. What am I doing? And I need an S. Okay. We were able to do this. We were able to merge them because they both have a name column. This one I meant to change because it's the exact same thing as up here. So sorry about that. Let's join pizza to another data set, pizza extra. So pizza extra does not have a name column, as you might have guessed. So joining them is pretty easy. Pizza join, pizza extra. Cool. Now we have flavored crust, yes or no, meal, and then heating method. Heating pizza in the microwave is very sad. Don't do it. Okay, so let's only join them together where all the data is present. So pizza, join, yes, someone said it. Yep, extra, how, right. You can also do, exactly, how inner. Both of those work. Can you join all three together? Yes. So pizza all, you have to store this. Pizza merge, pizza toppings. And then pizza all, join. Great, now we have lots of knowledge about pizza. Does everybody understand what's going on? Does everybody understand the difference between merge and join? Cool, okay. So we have one last section to get through before a nice 20-minute break. Pivoting. So you can pivot in pandas just like you can in Excel. So pivot tables are a good way to do some analysis on your data frame and see what's going on. So pivot table takes in 4 pieces of information, the data frame you're working on, the column to use for your index, the column you use for the rows, the column you use for the index, the column you use for the columns, and the column to use for the values. So we'll see what this means in a second. You can also pass in an ag_func parameter, so an aggregate function parameter that specifies what sort of mathematical operation to use on the data frame. It defaults to the mean. So let's look at what this means, because I think it's easier to understand when you see it. So here we have our pivot table function. We're going to use our AutoMPG data frame. We're going to take the mean of the weight for all combinations of the model and cylinders. So let me run this. Okay. So for everywhere in the data frame where the model is 70 and it has 4 cylinders, the mean value, the mean weight, I should say, is 2,292. I believe, I don't know what that, not pounds, probably like kilograms, I don't know, whatever. So everywhere in the data frame where the model is 71 and the number of cylinders is 4, the mean weight is 2,056. Everywhere in the data frame where the model is 76 and the number of cylinders is 6, it's 3,349. So this is just a way to aggregate and find descriptive statistical information about your data frame. If a cell contains not a number like it does here, that means that that specific combination, so in this case, where the model is 81, the number of cylinders is 4, there is no existing combination of that within the data frame, so you can't take a mean of something that doesn't exist, so returns not a number. You can pass in multiple column names to the rows, or to the index and the columns parameters, and this creates a multi-index. So let's see. We're going to add in origin to our index. And the way that you pass that in, you just pass it in a list. And we're still going to look at the mean of everything. So if we run this, whoop, It's the default aggregate function parameter. It's what it defaults to. We'll change that in a second. We'll look at different aggregates we can perform. So here we have two items in our index, model and origin. So in this case, where the model is 70, the origin is 1, the number of cylinders is 6, the mean weight is 2,710. So you can see how granular you can get with this and how really specific you can just throw everything into the index and the columns, and you can find out the mean of basically every combination of everything in your data frame. I'm not sure why you would want to do that, but it's possible. It's a good way to, again, do some exploratory analysis on your data frame. So you can apply different aggregate functions to your pivot table, and this is with the agfunc parameter. So here we have our pivot table function. I'm going to pass in our data frame. For values, we're going to pass in the weight. We're looking at the weight for everything. Model and cylinders again for the index and the columns. And this time we're going to look at the sum. So we're going to look at the total weight for every model cylinders combination within our data frame. So if we run this, you can see the sum, so the total weight for every car in our data frame, the model of 70 and cylinder of 4 is approximately 16,000. And again, it returns not a number where that combination doesn't exist. Does everybody understand this? Are there any questions? This can be a little tricky sometimes. Okay, so now we're going to create our own pivot tables. So let's take a few minutes and work through these. If you have a question, let me know. Come on. Also, you don't have to come up with your own pivot table because we are a little bit behind, so don't worry about that third exercise. Okay, how are we doing? Good? Anybody desperately need like one more minute? Good. Okay. Let's create a pivot table. To do tab completion, or well, to do, yeah, you just tab if you want to complete stuff. So we're going to use our data frame from before. Index is going to be column A. Columns are going to be, I believe, column J. And then values are going to be column H. Okay, nice little data frame. Again, the default aggregate function is the mean. So let's change the aggregate function to the standard deviation. Okay, so I just copied and pasted my line from above. Oop, whoa, fuck. Run this. Cool. That's the standard deviation for all of those combinations within the data frame. Okay, we're now going to make our own pivot table. So now we're going to switch over to our census data and do some fun stuff with that. We're going to take what we did with pandas and apply this in sort of a real world context. So if you all could click on that data analysis link right there, we'll open a new notebook. Okay, so let's start working through this. Starts off pretty basic, file IO, then we go on to selecting some stuff. Group by. Okay, so here's what we're going to do. We're going to work on this for a bit, then we're going to take a break, and we're going to come back and have 5 more minutes to work on this entire first section up to here, where it says go to the scikit-learn notebook. That's our next section. So yeah, start working through this section, and if you have any questions, let me know, and I will announce when it's time to take a break. Okay, at this point, we are going to take a 20-minute break. So if we could resume at 3:10, please feel free to keep working and or ask me questions. In the meantime, I will be hanging out here. But yeah, break. And we need probably a few more minutes. Yes, no, maybe. Who has made it to the end of this section? Oh, not very many people. Here. Okay. Okay. So do that again. Who has finished the section? Okay. Who has not finished the section? Okay. Let's take 5 more minutes then. Um, the end of this segment of this lesson section, we're going to be using this data frame to do some analysis on. So it's kind of important that we get there. Even if you want to skip some of the other sections, that's okay. We're going to extract a subset of our data set. So yeah, 4 more minutes. Okay. Oh, okay. Now how are we? Are we good? All right, let's go over this. Okay, so I already prepared the answers, so we can go over this a little bit faster. So to read in a file, read CSV, pretty straightforward. To look at the first 5 lines of the file, it's the head function. Column names, column attribute. Okay. Excuse me. To look at, to sort by age and then look at the last 5 lines. Sort function, pass in the name of our column, tail for the last 5. Okay. So if we're subsetting based on education, occupation, hours per week, looking at the first 5 lines of that, you can pass in a list of column names. Okay. Okay. We're creating a subset again. I used loc. You might have used iloc. That's okay. And remember, since loc is by label, it will grab that 100th row. I'm passing in a list of column names here and first 5. Okay, here's another subset. Education, num is greater than 8. And we're getting all the women from this data set, looking at the first 5 rows. This is Boolean indexing. So we have our first condition and our second condition, first 5 lines. Does that make sense? Cool. Group by, if you skip that, that's fine because I skipped that. Pivoting. So we're looking at what are our values? Oh, the mean hours per week worked by both female and male employees based on the number of years of education they've had. Does everybody understand what's going on with this one? Great. Okay. Sure. Do that. Do I need to make the font a little bit bigger for people in the back? Yeah. Yes, okay. Okay. Did anyone create a pivot table of their own choosing? No, yeah, I wouldn't either, it's okay. I didn't, clearly. Okay, so this is the important part. So for our machine learning section, we're going to run some classifiers on a subset of this data set. So we need to basically just Boolean index the crap out of this data frame. So we're going to take where native country is equal to the United States, hours per week worked is greater than 10, age is greater than 20 and less than 50, and then education is master's. Whoa, whoops. Double clicking edits the cell. Okay, so it's going to be a bunch of Boolean indexing. Let me see if I can, let me do this so you guys can see. Okay, so for this new data frame, we're going to Boolean index. So our first condition right here is where native country is equal to United States. Our second condition, hours per week worked is greater than 10. Third condition, age is less than 50 and also greater than 20. And finally, last condition, education is equal to master's. Did everybody come up with something like this? Yes? Okay. Does anyone need more time to look at this section right here? Yes, okay, cool. I wish I could make this display a little bit differently. So your data frame down here then should have the columns age, work class, education, education num. Basically, yes, all of the columns with the conditions applied. Okay. If you need more time with this, there is an answers file. So great. So now we have that. We're going to do one last pre-processing thing. That's this section down here. So, and I'll explain more of this in a moment. So scikit-learn, the way that it takes in data, it takes in the data, and then it takes in the labels for that data if you're classifying. So in this case, we have a bunch of data. What we're going to be trying to do is we're going to try and classify whether that person makes either greater or less than or equal to 50K in a year or greater than 50K in a year based on the data. So what we have to do, since this column is our labels, we have to split it off from the rest of the data frame. So this is just prep for the next section. So everybody go ahead and run this. Whoa, that's right, I need to run everything else probably. Just do this. It's gonna do a bunch of things. Okay. So we are here. Okay, has everybody run this cell successfully? No. It does. Yes, it does. You could do that as well. So you could do iloc -1. Yep. So you can negative index, and then this is all the labels. Any other questions? No. Okay. So now, yes? This doesn't work, 50_K? Ooh, interesting. Yes, that's right. Has to be with, are you, it should be in there. Or, I'm sorry, yeah. Should we be with loc? Are you running it with loc instead of iloc? Maybe. And it's still not working? It's not working. Okay. Let me come help you with that in just a moment. For now, let's move on. We won't need that file until later when we go back to it. So I will come help you at the next little lesson section, okay? Cool. So let's go to the scikit-learn notebook. Just click on that link. Whoa, that's not good. I'm in the, oh, I know why. I'm in my answers, haha. That's why. That's what happens when you look at the answers too soon. Okay, there we go. Right notebook. Okay, so I'm going to give you a brief introduction, a very brief introduction to machine learning. And as with all of the tools that we covered today, you could do a 6-hour tutorial on each of them, and it probably would not be enough to cover all of the cool things. Like in pandas, there's just a lot of cool things we can't get to. You can do even more complicated subsetting. There's a lot of time series analysis functionality. There's ways to apply functions to each row of a data frame and do something cool. We don't have time. So we're going to talk about machine learning in sort of a very short period of time. And a lot of this is just going to be me talking, but it's for the purpose of you understanding like what machine learning is and why it's useful and what we're going to do with it. So machine learning is the study and application of algorithms that learn from examples. So basically it's concerned with constructing systems that learn from data. So you have data, you give it to a machine learning algorithm, and it learns something useful from this data. And what it learns from this data, you can then apply to new forms of data. So for example, let's take a common example in the machine learning world of email spam. So when you get a spam email, it goes to your spam folder. If you get a spam email to your inbox and you manually mark it as spam, your email filter learns from that input and then will mark similar emails as spam in the future. It's basically taking some sort of input, learning from it, and then doing something with that knowledge. And spam emails are classified as spam emails because maybe they have like weird links in them, or they have an odd number of capital letters, or they're just not like nonsensical, or they're for inappropriate things, and like why would you be looking at that anyway? So basically, your email filter knows all of these reasons, applies them to each email that comes into your inbox and says, is this spam or not spam? Oh, it matches these criteria, it has weird capital letters, weird links, spam. Or it says, no, this email looks fine, not spam. So that's an example of machine learning. Your machine learns things and applies it. So it provides a way to essentially help us build better software by predicting more accurately on future inputs, on future data it receives. So, another common example is Netflix's recommender system, which if you have not rated any movies on Netflix, will give you some very weird recommendations. The more movies you rate, the more Netflix's recommender system actually learns and is like, oh, I'm gonna recommend to you movies that you might actually wanna watch. So there are some common terms in the machine learning world. When we say things like observation or data point or instance, we mean just that, like one piece of a data set, so like one row of a panda's data frame. When we say label or class in classification, which is what we're going to be focusing on today, that's what we aim to classify our new data as. So for example, we label emails as either spam or not spam. In our census data set, we're going to label each person as either less than or equal to 50K a year or greater than 50K a year. Features are what describe the data. So again, number of weird capital letters, number of weird links, number of known spam words. Those are features that would describe spam email. In our census data set, it's things like number of years of education, number of hours worked per week, and so on. Those are features. Categorical data is data that is discrete and finite. So, for example, job type. So in our census data set, there's whether you work in the private sector or the public sector or other, I think is one of the options. That's categorical data. It's data that refers to a specific category. Continuous data is numerical data. So if you think back to when we were working with pandas and whenever we did describe, we can only describe on numerical data. We can only describe on continuous data, which is basically simply subsets of real numbers. Take on any value between 2 points, basically like temperature or elevation. So there are two types of machine learning. We're going to focus on the first one today, but it's important to mention the other one. So the most commonly known type of machine learning is supervised learning. This is machine learning that makes use of labeled data. Once again, for example, the email spam example. Your email filter has seen thousands, maybe even millions examples of emails and knows exactly what is spam and what is not spam. Supervised learning uses past observations like all these emails your spam email filter has seen to make future predictions on all kinds of data. So again, there are two types, there are more, but the two main types of machine learning are classification and regression. So classification, once again, email spam. I'm going to hammer this point home. Email spam, classification, because you're classifying data into a category, spam or not spam. So the other type, regression, predicts the relationship between continuous variables. So for example, the relationship between temperature and elevation. As elevation goes up, you would expect temperature to decrease. Or something like the relationship between housing prices and square footage. As square footage increases, you would expect housing price to increase, which is definitely true in New York. Okay, unsupervised learning. Unsupervised learning is used when data is unlabeled. Maybe you don't know what you're looking for. It can be kind of an exploratory measure to sort of see what relationships exist within your data. So maybe you don't have something in your data set that designates whether something is spam or not spam. or maybe you don't know if someone makes over 50K or under 50K. So clustering, which is a type of unsupervised data, groups data into clusters in a way that observations in the same group are more similar to each other than to those in other groups. And dimensionality reduction can be a way to help us figure out what parts of our data are important. So exploratory measures can be useful as a precursor to supervised learning. We're going to focus on supervised learning today. And this is just like a super brief introduction. This stuff is super fun and very interesting, but we are running out of time. Oh, sorry. Okay. So my favorite tool for machine learning in Python is scikit-learn. It's an open source machine learning module. It's very comprehensive of machine learning algorithms. Pretty much everything I've ever wanted to do exists in scikit-learn. And it's also a project that's constantly being worked on. And it's a very active user community. A lot of people in the scientific Python community use scikit-learn. The documentation on the website is good, but you sort of need to have a basic grasp of machine learning, what machine learning is, to understand the documentation on the site. That was sort of a problem I ran into when I was first learning about these things. But there are tons of tutorials everywhere. I think there was a tutorial today, so if you wanted to focus on machine learning, you signed up for the wrong one because we only have like half an hour to talk about this stuff. But yeah, so lots of videos from previous PyCons, lots of guides, and so on. So why scikit-learn? Whenever we come across a new tool, we should ask ourselves, why should we use it? Why would you use this rather than MATLAB or R? Well, so scikit-learn is open source. It's free, unlike MATLAB, unless you're well connected. It's also currently the most comprehensive machine learning tool for Python. And since it's Python, unlike R, you can actually implement it into production or your app stack or anything like that. I've actually done that before, so scikit-learn, it's cool. There are also like a number of libraries that work well with scikit-learn, extend its capabilities. Pandas, scikit-learn can actually read in pandas data frames. Scikit-learn can also feed directly into matplotlib for graphing, which, spoiler, that's what we're going to do. So in this section, going to cover supervised learning. I have a section within this section for linear regression, but I'm not sure that we're going to be able to talk about it. We'll see. So we're going to talk about 3 classifiers. And then what we're going to do is see how they work, which is actually pretty easy in scikit-learn. Then we're going to go back to our census data set and try out these classifiers against our census data set and sort of evaluate which one might work better. Okay. So once again, classification classifies data into specific categories. Okay, so before we really get into this, let's say you have a whole data set and you train a model on your data set. If you try to test that model on the same data set, you're not going to be able to get a good idea of your model's accuracy because your model essentially knows the whole data set by heart. If you've trained it on the whole thing, it knows the whole thing. So what we're going to do whenever we use a new data set or use a new model, we're going to split up our data set into training sets and test sets. This is so we reserve a small portion of our data set to actually test the algorithm on. And then once we test it, we can actually compare it to what the actual answers are to see how well our classifier has done. So this avoids the problem of overfitting, which means that the model fits the data too well, which sounds great, but really it's not. Okay, so first algorithm, k-nearest neighbors. K-nearest neighbors finds a predetermined number of neighbor samples that are closest in distance, linear distance in this case, to a starting data point and makes predictions based on that distance. So basically, this model takes all of your data, sort of calculates how far away each point is from each other point, and says, okay, for new data, which group does the new data fit most closely into based on distance? So the normal distance measure for this is the Euclidean metric, which is a linear method. But you can actually throw in some other fun methods. yeah, again, it's useful when your data is linear in nature. It can be measured with a distance metric. If you start doing nonlinear things, it can get a little tricky, although there are ways to actually figure that out. So, like all algorithms, this one comes with a couple of caveats. So, if the classes in your data set are unevenly distributed, so for example, if you have like 100 spam examples and one non-spam example, the highest occurring label will tend to dominate the predictions. So that means if I have a data set of 101 emails and only one of them is non-spam, trying to predict on a new email is probably going to say it's spam, even if it's not. So that's one of the caveats with k-nearest neighbors. Also, choosing k can be tricky. Choosing k is very difficult. So k is the number of essentially groups that you want to classify into. We'll just go with the defaults today. So, okay, so let's actually do some of this. As we go through all of these examples, you notice that the basic fitting and predicting process and then evaluating process is the same, which is good because it makes it really easy to try out a bunch of models at once and see what's going on. So first, we're going to split up our data set because, again, we don't want to overfit our model. So we're going to use our wine data set again down here. And I've already, so before if you remember in our census, when we were doing our census data set work, we split off that last column from the whole data frame. That's so we have one data frame of data and then one data frame of the labels that fit with that data. So I have already, for the wine data set, I've split off the labels from the wine data set. And if you remember, there are 3 groups in the wine data set: group 1, group 2, and group 3. And that's what we're going to try and classify data as in the wine data set. So, once again, we import pandas because pandas is the easiest way to read in files. From sklearn.crossvalidation, we're importing train test split, which is the nice function that will split up our data set. Here we're reading in the data. Here we're reading in the labels. We need to squeeze this because otherwise it gets really funky. I can give a better definition for that in like when we break because we are vastly behind at this point. So take my word for it for now. So here we go. So we create training data set, training test, or data test set. Then we split up the labels into the training and the test. And to do this, we have our train test split function. We pass in the data, we pass in the labels. You can change the parameter for how much of the data is split. The default is 75% into the training set and then 25% into the test set. But you can change that if you really want to. We're going to leave it as it is. Just run that. Cool. So once again, scikit-learn can actually understand pandas data frames, which is pretty cool, and I think is only the newest release or so of that. So if we look at just one row, here's the first row in our training set. You notice that it's actually the 50th row, or the 51st row, if you want, however you want to talk about it. That's because the way that it splits up the data is it splits it up randomly. So we're selecting 75% randomly from this data set. So we're not just taking the first like 75% and throwing it, because that would not be a very good way to select data. So we select it randomly. In fact, if we do this again, we get a different row. It's random. Okay. Your row. Okay, so if you're running an earlier version of either scikit-learn, pandas, or IPython notebook, this might look different. So do you know what version you're on? Of scikit-learn. Oh, you mean of IPython notebook? Oh, Python, yeah. Okay. Let me know if the rest of it doesn't work, and I will come help you. Okay, so just to compare the length of the original data frame and the training set, so here's our original data set, and here's our training set. We run this. Okay, yes, this one is shorter. That's good. We wanted that. Okay, so now we can fit our k nearest neighbors classifier to our training set. This is very, very straightforward and easy. First, we create our estimator object, then we use the fit function to fit the algorithm to our data. So from sklearn.neighbors, we're going to import k nearest neighbors classifier. We create our estimator object right here, setting k nearest neighbors classifier equal to just knn, easy to remember. Then we fit our data. So knn, we use the fit function, we pass in our training set. So we pass in the training data as well as the training labels. And the algorithm is going to take in this data, learn the relationships between the data itself as well as the labels, and then it will be able to extrapolate that to our test set. So let's run this. It just prints out, oh, okay, here's our classifier, and then these are the default parameters for that classifier. Now we're going to predict. So here are the predictions. So this is really easy. So we take our estimator object, we use the predict function, and we pass in our test set. And the output of that is an array of labels. So remember, our wine types are either type 1, type 2, or type 3. So what this model has done is it's taken our test set and it's said, okay, I'm going to predict that the first wine in the set gets a label of 1, the second wine gets a label of 2, third gets a label of 2, and so on and so forth. The good news is that since we had labeled data, we can actually compare it to what the real labels are. This doesn't print out in a way that's conducive to comparing them, so if we scroll down, we can actually calculate how accurate our classifier is. We can do this using cross-validation, which is a great method for essentially validating how accurate your model is. Excuse me. Okay. So cross-validation takes in your entire data set and your entire label set. It randomly splits it into training sets and test sets, trains it on the training set, tests it on the test set, and computes how accurate the model is by checking the predicted labels against the real labels. And it does this multiple times. So the default for scikit-learn is 4 times. We're going to do it 5 times because why not? But it splits up the data set randomly each time that it runs this cross-validation method. So each split is going to be different. And this is a good way to get a better assessment of how well your model does. So this function takes several parameters. First, you want to pass in the model, knn. Next, you want to pass in the whole data set. So we split it before, but we don't need to pass in the split stuff because it's going to split it up. So we pass in the data, we pass in the labels, and if you want to change the default value of cross-validation, it's the CV parameter. So we're going to change it to 5. Text below sort of spoils it, but there we go. So after cross-validating 5 times, our model is approximately 70% accurate, which is pretty bad. But that's just a very straightforward way of training a model, predicting on it, and then validating the results. So now you're going to do this. We're going to use scikit-learn's built-in data sets. Scikit-learn is pretty cool in that respect. It comes with some built-in data sets that you can just play around with. We're going to use the iris data set. So here I have, I've loaded it in for you, and I've split the data and the labels. So if you go ahead and complete the rest of this section, and we'll come back in a few minutes. Okay, let's go over this. So, to split up the data, this is our train test split function. You can call your variables whatever you want to call them. Okay, and then we just pass in data and the labels. Whoop, what did I do? Oops, I think I meant to say labels here. Cool, okay. Now we're going to train our model. So I'm going to just create a new one. Okay, so we're going to fit it to our training data as well as training labels. Okay, prints out the default parameters. Now let's make some predictions. Predict function on the test data. Okay, cool. I'm going to skip that because we're just going to cross-validate to see how good it is. So, cross-val score takes in the model, the whole data set, whole label set, and then let's do it 5 times. Okay, so it's pretty good. The built-in data sets within scikit-learn are very clean and nice and evenly distributed, so they will do well with whatever classifier you choose to use. Okay, let's talk about decision trees. Decision trees are another fun predictive model. They learn very simple decision rules based on the features within your data set. So it looks at the features and it says, why is this feature for this particular observation? Learns those relationships, and then decision trees will map those observations about map observations about an item to conclusions about the item's target value or label. In this case, we're trying to figure out, in our census case, we're trying to figure out if someone makes less than or equal to 50K or over 50K. So decision trees will figure out, okay, so this feature relates to this feature in this way, and says, okay, so this is why this happens. And then it applies that relationship to new data. So decision trees are sort of structured like trees in that leaves represent class labels and branches represent conjunctions of features that lead to those class labels. So trees are cool because they can handle multiple types of data really well. So once again, in our census data set, we have both continuous data, like ages, but also we have categorical data, like the type of someone's job. So decision trees are really great for that kind of data. However, they can be very simple in nature and can lack the ability to capture rich relationships within your data set. So we're basically going to do the same thing we just did with a different classifier. Okay, so from sklearn.tree, import decision tree classifier. Here we create our tree model. Once again, we're going to fit it to our training. We're going to use our wine set again, fit it to our training set, and we're going to predict on it. Okay? Real labels, okay. Probably don't need to do that, whatever. And do this 4 times. And you can see, so if you remember in our wine set, scroll up. Actually, I don't think I have it in here. That's okay. Whoop, where'd I go? Right. So this classifier is actually a much better fit for our data set. It is much more accurate than k-nearest neighbors, which had an accuracy of about 70%. It's about 87% or so. So better improvement. And knowing the different types of data that a classifier can deal with is very important for determining which classifier works best with your data set. So we're going to take maybe 2 minutes and just do that whole process again. So go ahead. Yeah, and once again, if you are using Wakari, this section is not on Wakari because Wakari does not seem to want to upload the newest version of IPython notebooks. So, something to keep in mind. Okay, let's go over this. It's pretty straightforward. Once again, we're going to split up the data. So we're using a digits data set, which classifies a handwritten digit into numbers 0 through 9. So let's see. Okay, so data, digits labels. Okay, pretty simple. Going to fit it. Okay, let's do. Okay. Now we're going to pass in our training set. Fit that, prints out the default parameters. Predict on the test. Prints out the predictions. Okay. Finally, let's see how well this classifier does on this set. Okay, so 80%, maybe a little bit less. So decent, but not great. Okay, the final classifier that we're going to talk about before we jump over to our census data section and actually do some of this with some real-world data is the naive Bayes classifier. This is a probabilistic classifier based on Bayes' theorem, which essentially says that every feature within your data set being a certain way is unrelated to every other feature. So basically, so if we were referring to email spam again, the number of capital letters in your data set has nothing to do with the number of weird links in your data set. And whether or not that's true, it makes that assumption, which is a naive assumption, hence the naive in the name, because that doesn't always hold true in reality. We all know that things will affect other things, even when we don't expect it. So that's why there's a lot of other pre-processing work you can do to discover that those sorts of relationships. We don't have time to do that. So despite this oversimplification of assumptions, the classifier performs pretty well, and even quite well, especially if we're talking about like document classification. So naive Bayes is good when your features are independent and your data is normally distributed, though more sophisticated methods generally perform a little bit better because of how naive this method is. So, as you might expect, this works exactly as it did the first 2 times. Great. Here we have sklearn.naive Bayes. We're importing Gaussian naive Bayes, fitting it, predicting on it. Okay, let's skip that. So, once again, we're going to cross-validate to see how accurate our model is. Does pretty well. Does, I think, the best out of all 3 of the classifiers on the wine data set. So that's kind of interesting to think about. Okay, so let's, once again, take like a brief 2 minutes, just do this one more time, and then we will jump over to our census set and actually see what sort of interesting things we can find there. Okay, I'm going to start filling this in. So we've actually already split up this data set, so we don't need to split it again. Let's fit it to our data though. So let's see. Just going to create a new one. Probably put the other one in there first. Okay, so we fit it on our training training data and training labels. Okay. And let's see how this one does in comparison to the previous example. Digits data, digits labels, and let's do it 5 times. Okay, not so good. So we are now going to skip the linear regression section because, yep, awesome. That's super fun though, if you want to do that on your own time. Okay, so now we're going to jump back over to our census data. Okay. This is the fun part, I promise. So we're going to put a couple of final pre-processing touches on our data that we worked with before. I'm going to walk you through this because it's be a little tricky. So one thing about scikit-learn that can be frustrating is that it takes in continuous data only, which means that if you have categorical data in your data set, like we do in our census set, you'll need to transform it into something that the scikit-learn estimators can actually handle and deal with. So this is not as bad as it sounds. So we're basically going to take our data frame and then encode the categorical data into arrays of 1s and 0s. So the first thing we have to do, and everything in this first section, you can just run each of the cells. So, and I'll explain what's going on. So we first have to transform our data frame into a dictionary before we can vectorize the data within the data frame. So we first have to transpose the data frame. That's right here. And that just flips it so there's 1 row per nested dictionary. And then we'll put each of these items into a list because scikit learns the dict vectorizer object, which is what looks at this, takes in a list of dictionaries to encode. So we also only need the values. So if you just run this cell, oh, I probably need to run, what did I miss? Oh, that's right. I was working in this one. Nope, this one. Sorry about that. Okay. Right, this one. Okay. So that'll run. It might take a minute, working with a lot of data. So now we're going to encode those using dict vectorizer. And this just basically takes the data, it transforms it. So we import from feature extraction our dict vectorizer object. We create our encoding object, and then we're going to transform it. So we use fit transform on our census data, and we stick it into an array. And this, again, this takes the categorical data that's present within our data frame, like the type of job someone has, and encodes it into an array of ones and zeros. Okay, so we do that. And you can see there are ones and zeros in there now. After that, if you remember, we also have those labels, either less than or equal to 50K or greater than 50K. These are categorical labels, so we need to encode them. So once again, scikit-learn can actually handle them. So that's pretty easy with label encoder. So from preprocessing, we import label encoder. We create our encoder object right here. Once again, we use fit transform on the labels. And you can see we have zeros and ones. So 0 for less than or equal to 50K, and 1 for greater than 50K. Okay, so those are the final preprocessing steps. So, whoops, don't look at the answers. Flip back to this one. So now we're just going to work through the next sections all the way up to down here when it says to go to the matplotlib notebook. So let's take 5 or so minutes to work through that. If you have any questions, should be good. Don't forget the variable names you're working with now, transform data, and transform labels. That was a really good point. If anyone's on Python 3 of any kind, you have to change iter items to just items. I don't know if anyone else is running Python 3 in here. Otherwise, this section might not work. So, okay, how are we doing? Do we need another minute or are we pretty much done? Nope, another minute. Got it. Okay. Now are we ready to come back? Okay. So to split up our transformed sets, boom, split them. Awesome. Train test split on transform data and transform labels. Okay, so now we're going to just fit and predict all three classifiers on this data. So k-nearest neighbor, decision tree, and our naive Bayes classifier. So we create each estimator object. Then we use the fit function. We're fitting it to our training set. So census train and labels train for all three of those. Now we're going to predict. So let's look at the output of k-nearest neighbors. It's going to take a minute because it's doing a bunch of things. Okay, cool, interesting. Let's see what happens for our tree. You can see that there's some discrepancy between what k-nearest neighbors predicted as well as what tree predicted, decision tree predicted. And I should mention that your results are going to be different from mine because your train test split has probably selected a different random subset than mine. It'd be very interesting if it didn't. And finally, naive Bayes. Again, much different. So let's cross-validate each. Let's see which one actually is the most accurate. So we use cross-val score. Once again, we pass in our model. Oh, sorry, yes? Sure. Because if it uses the test set, it's still going to split it into training and test sets. So then you're cross-validating on an even smaller portion of your data set. You want... No, when you pass... Right, okay, yeah. Yeah, so when you pass in this model, it takes it just as it is. And then when it splits the data sets, it retrains it. So it gets rid of what it had before. It throws out that knowledge. I think there's a way to specify to like retain history when doing this, but it throws out the previous knowledge that it had, retrains, and tests. And it does that every single time it cross-validates. So first step, splits the data, trains it, tests it. Okay, throws out that knowledge. Second step, splits the data set, trains it again, clean slate. Yeah, so that's basically... Yep, 5 times. Yeah. Oh, that's okay. Yeah. So the purpose is to basically, so when it splits the data set, it splits it randomly. And this is to capture like a more complete picture of your data set because it's possible that if you just do train test split and you split up your data set, like if your examples are maybe ordered by class, so you have all the 1s and then all the 2s and then all the 3s, like maybe when you split it, you have 1s and 2s in your training set and then 3s in your test set, it's going to, like, you're not going to, basically that class doesn't exist in your training set because it split it like in order. So when it splits it randomly. When it cross-validates, it splits it randomly every single time it runs a cross-validation cycle.
So my question would be, is there a function in scikit-learn to take your predictions and your test labels and do a comparison and give you like how well it did? Or?
Yeah, that's the final step of cross-validation. So when it trains on the test set, but then the scores. Oh, yes, yes. Yes. That function is called the score function. And what you do is you pass in your test set as well as your test labels. And then it compares. Yeah. So cross-validation is like basically scoring it 5 times. But again, it really determines like the split in your data set. And that's why it's important to cross-validate multiple times because like you see here, on this particular split of data, it got an accuracy score of 50%, which is not good. But down here, and that's naive Bayes. So when we get to this section, you can see that we actually have like a much wider variety of scores. So that's why we cross-validate. It's essentially taking a score, but it's taking a score multiple times with random splits of the data. Does that make sense? Oh. Oh, you mean like actually like pass in a bunch of models and have it output like which one did the best? Yeah, I think there's actually a way. I'm not sure if I know it off the top of my head, but I think you can actually cross-validate using like the models as input, like a bunch of models as input, and then it outputs the one that scores the highest. I need to look into that actually. That's a really good question. Okay, so once again, cross-validation, pass in the model, the whole data set, the number of times you want to cross-validate, runs. Just going to rerun all of these. Okay, so then we can see which one does the best. So we're cross-validating on each. Okay, so this one, k-nearest neighbors, not too bad. We have a lot of variance in our scores, which means that we need to more finely tune our models. That's okay. Decision trees has very wide variance in scores from 32% to 75%. That's not good. And then naive Bayes also did mediocre. So this sort of tells us that we need to do a few more processing steps on our data set before we try running models on it. Generally, if you're getting like very widely varied results like this, it's a sign that maybe you don't need all of the features in your data set. Maybe some of them are noisy. Fortunately, that is all the time for machine learning we have today. So now we're going to talk about visualization very briefly. So there should be a link in there. Jump over to the Matplotlib notebook to jump from the correct notebook this time. Okay. And everybody, make sure you run this little cell right at the top. It says %sign matplotlib inline. If it's in Wakari, it might say pylab inline. Just make sure you run that. This makes the IPython notebook actually produce the plot within the notebook and not outside of it. Okay, Matplotlib. And at a higher level, the importance of communicating your results. So you've done your preprocessing and you've done your analysis. Sorry. I just noticed a typo and I got very annoyed. Yep, typo. Anyway, you've done your analysis. Now, generally, you don't live in a bubble and that the process just ends there. You're probably going to have to communicate your results in some way to someone. And often you're going to be communicating your results to people who are not programmers or machine learning experts or statisticians. So data visualization is a really good way to present your findings in a meaningful way, because often it's super easy to just look at a plot and say, oh, I can see exactly what's going on. This variable has a higher distribution level than these variables, and so on. It allows you to literally see what's going on in your data. And also, data visualization can be a really great exploratory step. Like if you're curious about the distribution before you even start working on your data set, it also can be really good to do at the beginning. So one of the most important parts of data visualization is choosing the best plot for your data. This is not a trivial task. There's a lot of different theories about visualization out there. But most importantly, it doesn't have to be fancy or complicated. It just has to get the point across in a clear manner. So what is Matplotlib? Matplotlib is a two-dimensional visualization library that is very widely used, especially in the scientific Python community. It's very customizable, can create a wide variety of plots, and you can easily feed in data from other Python libraries like NumPy, SciPy, scikit-learn, pandas, and so on. There's a lot of resources online for learning more about this, and the documentation is pretty good. I should mention that I am not a huge fan of Matplotlib because it can be very convoluted and not very user-friendly, but it's like probably the most popular visualization tool at this point. There are some other really great visualization libraries out there for Python, but right now Matplotlib is most extensive in terms of scientific graphing stuff. Okay, so this section, these are all like very simple, uncomplicated examples. Then eventually we'll go back to our census section. Okay, so let's make a scatter plot of our wine data of the ABV and color features. So we're going to use pandas for this to read in our data because, again, reading data into pandas is super easy. So this line, we're going to import matplotlib.pyplot as PLT. This is pretty standard matplotlib importing convention. We're going to read in our wine data set with read CSV, as we've been doing all along. Then we're going to make a scatter plot. So here I'm accessing the column from the data frame as an attribute, wine ABV and wine color. If we do this, we get a nice little scatter plot. And the first parameter is the x-axis. So ABV is along the bottom, and color is along the y-axis. And it's possible to add labels, as we'll see in a minute. It's also possible to feed in data from scikit-learn. I'm going to briefly walk you through linear regression, and then we're going to see how this works in terms of visualization. So once again, linear regression is modeling the relationship between continuous variables. In this case, we're going to look at magnesium against ABV. So here, I'm just subsetting my wine data set into two parts, magnesium and then ABV. I'm going to train test split because we always train test split, create my linear regression model, and then fit the training set to the linear regression. Okay, just going to do that. Now we're going to plot that. We're going to actually see what it looks like. So the first thing we're going to do is we're going to throw all of the points onto the graph because we want to see all of the points in relation to the linear regression line. So we're going to scatter magnesium and ABV. So here from the magnesium subset I took, I'm using magnesium. Here I'm taking the ABV column, and then we're going to make those points black. And then we're going to plot the linear regression line. So to plot the line, this right here is our test. We're going to run the predictions on the test, and then we're going to make this line green, and we're going to make the line a little bit bigger. That's what this line width function does. Okay, so if we run this, okay, cool. So now here's the scatter plot of our data, all the dots, and then this is the linear regression line that our predictor came up with. So that can be a really interesting way to see the actual data versus your predictions. So another easy plot to make is a bar chart. I'm first going to show you this in Matplotlib, and then Pandas actually has a really nice wrapper around Matplotlib, which is a little easier to work with in this context. So the first thing we're going to do, we're going to basically calculate the counts of the number of wines for each wine type we have. So if you remember, we have 3 wine types, type 1, type 2, and type 3. So we're going to get value counts. And you can count values in any data frame really easy with value counts. And I'm only grabbing the wine type, all the data for the wine type column. So to make a bar chart, we use the bar function. We do wine type, which is the data frame we just created, and take the index, which is the type. Then we're going to take the values, which are the counts. Then plt.show makes it show. Okay, now we have a bar chart. Not too bad. This is great, but see how the x-axis has numbers in increments of 0.5? This is because this bar function up here is expecting continuous input. It doesn't really understand categorical input. So there's actually a much easier way for this situation. Pandas has a nice wraparound Matplotlib for this specific purpose. So if we want to do the same chart in pandas, this is why pandas is super great. We take our wine type. If you remember wine type, we made the value counts. Actually, let me just show you what that looks like. Value counts of each wine type. So we have 71 of type 2, 59 of type 1, 48 of type 3. And in pandas, you can do the in this case, series, the plot function, and we want to make a bar plot, bar chart. So again, it's a wrapper around matplotlib. And now we have 2, 1, and 3. And you can obviously change. It's a little bit hard to read horizontal numbers. Yeah, but we have a decent value distribution here. Making a histogram, also fairly simple. Okay, we have 8 minutes left. Awesome. So histogram. Once again, we're going to subset. We're just going to take the ABV column. You can make a histogram with the hist function, pass in our data frame that we just created of just the ABV column. We're going to make 14 bins, and we're going to make it red. Okay, so here's a nice little histogram. You can look at the distribution again. Okay, pretty normal, not too bad. Okay, I'm going to skip this. This is just, we're looking at, actually, no, I'm not going to skip this because this is kind of cool. So, what we're going to do is we're going to look at the predicted values for wine type against the real values for wine type. So we're going to make a bar chart that compares each side by side. So right here, we're just creating our classifier. And an important thing to note is that at the end of this, I'm throwing my predictions into a list. This is important. So we do that. Now we're going to take accounts of each wine type in the set. So we're also going to offset the x values so you can actually see the bars next to each other. So this right here, this is the offsetting. So we're going to have, so we have 3 wine types, type 1, type 2, and type 3. We're going to offset the real values just by a little bit so we can actually see the bars next to each other. And you'll see this in a moment. So we're getting our counts for our predictions, which right here, predictions, we made a list of our predictions. So now we're counting the values. We take our actual labels and we're going to throw them into a list. And then we're going to get counts right here of that list of labels as well. So now we're going to plot this. If I run this, and now you can see, let's see, yes, green is the real labels, or no. Right, yeah, green is the real labels, and blue is the predicted labels. So that's just a very interesting way of looking at your predictions versus the actual labels. So you can print them out, you can cross-validate, but sometimes it just helps to see like what's going on. There are multiple ways to customize your plot. We have 6 minutes, so take my word for it. Let's see what this does. Oh, look, it's purple. Let's look at this one. You can actually add labels to your axes, which is really useful. That's really simple. After you make the plot, you can do X label and then pass in what you want to do for the X label. Same thing with Y label. You can change the type of line, and the type of point. So here, I don't know if you can see that, we have stars for the blue points and then a triangle line. Not sure why you'd want to do this, but it's something interesting to know about regarding matplotlib. Okay, and then you can also add a legend. So that's with legend. We've stored the scatter plot data in a variable, pass that in as well as the label, and then creates a nice little legend for you. So that can be useful. Okay, I'll leave it up to you. We have 5 minutes left. Do you want to work through this or do you want to ask questions? Who wants to work through this? Raise your hand. Very high so I can see you. One lone soul wants to work through this. Great. Who wants to ask questions? 2 lone souls. Okay.
Who wants to leave?
Who wants to leave early? No. Okay, how about this? We're going to end. If you want to ask me questions, come up and ask me questions. I will answer the questions that you put in the question doc, which you all have access to. Other than that, I hope you go off and actually finish the matplotlib section. Yeah, if you like I said, if you have any questions, let me know. I'm on Twitter at Sarah_Guido. That's in the README of the GitHub repo. And other than that, thanks for coming, and I hope you enjoy PyCon.